Okay, welcome to ME 3501 Simply Supported Beam Experiment. So in this particular experiment, you're going to have a beam that's simply supported. That means it has pin supports on both ends. So this is the fixed support on this apparatus. It's been moved all the way to the side over here. These are the two pin supports that we're going to be using. And these pin supports have an interesting structure. Built into the pin support is a little it's a dial gauge, dial caliper basically, which measures the displacement of this end over here and converts that into load. So there's a calibrated spring on each one of these supports, and each millimeter of displacement of the support corresponds to 10 newtons of force. So that permits you to calculate the reaction force at each one of the supports. However, you have to be aware of the fact that the way that the supports calculate the reaction force is by deforming downwards. Okay, so this is one of the classic conundrums of experimental mechanics, is sometimes the instrument that you're using to make a measurement affects the experiment, right? In physics, the ultimate example of that is the Heisenberg uncertainty principle, where the thing that you're using to measure velocity or position actually changes the other one. In this particular case, we're not that, we're at that level of accuracy, obviously, but the fact that we're using displacement of the location of the support to measure the reaction force means that you have to be careful when you're calculating the center displacement of the beam. Okay, so what we're going to do is first we're going to remove these fixed supports. You can have a pin in them, which means that it doesn't displace downward at all. So the plus side of that is that the support is then rigid, but then you don't get the reaction force. So what we're going to do is we're going to remove those pins. So now the support is no longer rigid. It will displace downwards under load, but the plus side of it is that now you can get the reaction forces. So I'm going to make both of the pins be not rigid. I'm removing these pin supports, the pins from the pin supports, so that they can move up and down. Now I'm going to try to center my beam as much as possible on the two pin supports. If you have different amounts of overhang, then that results in asymmetric supports, the reactions at the supports. So I'm going to center the beam as much as I can on the two supports. And then what I'm going to do is I'm going to zero out the reading on each one of these supports, so that the baseline for the whole thing is when the beam is sitting on them, but it doesn't have any loads applied to it. The other thing that you're going to need to do is you're going to need to make sure that your beam isn't tilted. So each one of these has a height adjustment to it, and the way that I'm going to do that is I'm going to move this dial gauge over here and put it dead center on this beam, and then move the dial gauge down and clamp it. I'm going to turn it on and zero the dial gauge over here. So now this is measuring the level of the beam on this side. So now if I move the dial gauge and put it dead center on the other support, it should also read 0 if the beam is not tilted. So I'm going to put this one dead center on the other side. And it's not reading 0. You notice it's at minus 0.35 millimeters. So I need to adjust the height of this so that it reads 0. And so now that's reading 0 millimeters on that side and 0 millimeters on the other side, hopefully still. Let's check that. Okay, it's 0.03 millimeters on this side. I'm going to make it just a tiny touch adjustment there. That's 0 now. Okay, perfect. So now the two sides of this beam are level with each other, and I'm going to put this support is at 300 millimeters. This support is at 1,300 millimeters. The average of that is 800. So I'm going to align this with the 800 millimeter location and zero the displacement of the beam. Okay, so now I'm reading displacement at the center point of the beam, and that displacement is set to be 0 when there is no load on it. Let me zero out my reactions as well. The reactions had a tiny positive reading because this is now pressing down on the beam just a little bit. So now what I'm going to do is, this is a 4-point experiment. So I'm going to put 2 hangers on the beam at standard locations, and then we're going to load those hangers with the same amount of load and incrementally increase that. And then you're going to use your strength of materials calculations to calculate, as a function of the load at the 2 loading points, what the central deflection is going to be. And again, in your calculations, take into account the fact that when we take the readings at the support points, those readings represent not just the reaction load, but also they represent the displacement of the support point downward under the load. If you don't take that into account appropriately, you're going to get very large errors in your modulus, whereas you shouldn't. This experiment should result in fairly low errors, okay? So what I'm going to do is I'm going to put the hangers on the beam at the locations where they're supposed to go. 600 and 1,000. Okay, so we are set up now, and I put the load hangers on. So actually, I guess we should zero out the load hangers as well. So let's zero out the central displacement with the load hanger in place, zero out the load / displacement at each reaction point with the load hangers in place. And now I put symmetrical loads on each one of these hangers. Careful not to nudge the hanger from its location. And then, having placed those loads on there, we're going to take readings at each one of the 2 supports and readings at the center, and then pass that information on to you. And from that, you should be able to, using your point bending calculations, come up with experimental results for what the modulus of elasticity is, and compare those to what the modulus of elasticity for steel actually is.